Hello, I'm Mr. McBrien. This is TEJ20, unit conversion. So today we're going to talk about the importance of units. We're going to talk about how to convert units using the multiply by 1 trick. So first off, we might ask ourselves, why even bother converting units? Well, for starters, our equations only work. They're only correct if we use the right units. If we choose the wrong units, an equation no longer applies. So that's one reason. Another good reason is communication. So the United States of America still uses imperial measurements like inches and miles, like Canada used to back in the Dark Ages. And so we need to be able to convert between these things if we want to communicate with our friends below the border. Humans like to converse using numbers between 1 and 999. Sometimes numbers are really small or really large. In order to be able to communicate with numbers between 1 and 1,000, we have to make conversions. We have to add prefixes. Sometimes the units we start with aren't appropriate for communicating the result we want to communicate. And for this reason, we've got to be able to change units. Now, unit conversions are important in terms of their accuracy. So I've got a few examples here of when things didn't go so well with converting units. So back in 1983, a Boeing 767 took off from Montreal. And unfortunately, the crew put less than half the amount of fuel they were supposed to into the jet. So over Manitoba, they found themselves without any fuel and had to actually glide to an unused airstrip, which was being used as a drag race track. And they managed to glide the plane in, and really the only reason there were no casualties was the pilot was actually very skilled as a glider pilot, an unusual skill in a 767 pilot for sure. 16 years later, $125 million Mars probe was lost because, unfortunately, one of the American teams used imperial measurements and another team used metric. And so they did some calculations about what they needed to do, and instead of going into orbit around Mars, it slammed into the surface of the planet. Definitely a disappointing result. So unit conversions are important. We need to be able to make those conversions effectively. Let's talk about Ohm's law for a second. We all know now that I is equal to V divided by R. In fact, these equations, that equation only works if we're careful about our units. So current's only equal to potential divided by resistance exactly if our units are amperes for current, volts for potential, and resistance ohms. If we're given any other units, we can't use our equation as is. By the way, if we want to communicate the thickness of a dime, it's quite effective to communicate in millimeters, 1.35 millimeters. However, in other instances, we may need to be able to talk about that thickness in other units, especially meters. If we want to talk about, for example, how fast heat flows, we might have a calculation in meters per second. And then we'd need meters for that thickness. But if I'm trying to communicate to you what the thickness of a dime is, which would you rather hear? 1.35 millimeters, 0.00135 meters, or 0.0000135 kilometers? In fact, we probably want to hear that 1.35 millimeters. That imperial to metric conversion that caused so much trouble with the Gimli Glider and the Mars probe, F is equal to ma only if the units are consistent. So if we want to accelerate a 200-pound astronaut at 10 meters per second squared, we need to know the astronaut's weight in kilograms, not pounds. Now the good news here, for all of these conversions, one tool solves the problem. So we only need our single tool to be able to solve all of these issues. Now to illustrate this, I'd invite you to think about for a second your grade 3 arithmetic. What happens to a number when we multiply by 1? The answer, of course, is the number stays the same. In fact, the same thing happens if we divide by 1. 9 divided by 1 is equal to 9. So, if we multiply or divide by 1, we still have the same thing. We haven't altered it in any way. So, we can use this trick to do unit conversions if we have one small additional piece of information. And this multiply by 1 concept is the one I want you to master today. Okay, since any number divided by itself is 1, we can actually rearrange a simple statement to give us the key answer. So let's take 1 inch is equal to 2.54 centimeters. We can divide both sides by 1 inch. The left-hand side, 1 inch divided by 1 inch. The right-hand side, 2.5 centimeters divided by 1 inch. Now, as soon as we do this, we should recognize what's on the right-hand side. 1 inch divided by 1 inch is equal to 1. Or 2.5 centimeters divided by 1 inch is equal to 1. Okay, this is interesting. We now have an expression of 1 is equal to 2.54 centimeters over 1 inch that came from 1 inch equals 2.5 centimeters. Now we can use this. So, if we know that a compact disc is 4.7 inches across, we can get that value in centimeters using our multiply by 1 trick. So we're given D is equal to 4.7 inches. We can look up in a table 1 inch is equal to 2.5 centimeters. Now all we have to do is multiply by 1. So we multiply by that ratio, and here's the only remaining trick. Make sure that the unit that you want to keep is on top. So we want to keep centimeters. That's the result we want to see, so we keep centimeters on top. So our D is equal to 4.7 inches times 1, or times 2.54 over 1 inch. So the centimeters is on top like we want. Now for those of you who are good at algebra, you can cancel out the inches, but you know it's going to cancel anyway. So inches divided by inches, this cancels away, and the only units remaining is centimeters. 4.7 inches is roughly is roughly 12 centimeters. So a CD is 12 centimeters across. Now, does that make sense? Well, you know a centimeter is roughly the width of your finger. Does it make sense that a CD would be 12 centimeters across, or 12 widths of your finger? Yeah, it's approximately correct. You know that's about right, so you can go ahead and underline it. Okay, let's try a distance calculation then, not resistance. So a friend invites you on a 5-kilometer run. What's that distance in meters? Well, our given is a distance of 5 kilometers. You might know that 1 kilometer is equal to 1,000 meters. And our unknown is the distance in meters. Again, we can take our 5 kilometers and multiply by 1. Notice this time meters is on the top. That's the unit we want to keep. Kilometers is on the bottom. That's the unit we want to get rid of. So 5 kilometers times 1,000 meters divided by 1 kilometer. And our answer is 5,000 meters. Now, does that make sense that a 5-kilometer run would be 5,000 meters? Well, meters about one pace, so sure, 5,000 steps. So that makes sense. Okay. Now, the thing that we're lacking right now is some of the conversion types we're going to use in computer engineering. So what we have are some prefixes here. We're not going to typically convert between imperial and metric. Instead, we're going to convert between numbers that have prefixes and numbers that don't. So the prefix capital M, we say mega, and the multiplier is 1 million. We already covered kilo. Multiplier is 1,000. Milli, notice the small m instead of the capital M, gives us 0.01. Micro and nano. Okay. Now we can modify our table a little bit to, if not make the multiply by 1 technique more effective, at least make the numbers a little easier to manage. So this is a modification of the table where on the top we've still got 1 million ohms per mega ohm, 1,000 ohms per kilo ohm, as we had in the previous one, but we've inverted the other ones. Remember, it's multiply by 1 technique, so they're still equal either way. We have 1,000 milliohms per ohm, 1 million microohms per ohm, 1 billion nanoohms per ohm. You'll still invert this as you need to, but you should find this useful when you're doing your multiply by 1 technique. So 1,000 milliohms per ohm is still equal to 1. Okay, so let's try an example from computer engineering then. Let's say we wanted to apply Ohm's law to a circuit with very low current. So to light our LED, we need 35 milliamps of current. What resistance do we need with our 9-volt battery? So we're given I is equal to 35 milliamps and potential V is equal to 9 volts. Our unknown is R, and we know I equals V over R. And we have to rearrange this. Remember, use your algebra. So resistance is equal to V over I. The problem is this equation only applies if there's no prefixes on these numbers. So we got to get rid of this prefix on the milliamps. Okay, so now it's time for our multiply by 1 trick. 1 amp is equal to 1,000 milliamps. We can then rearrange that to be 1 amp per 1,000 milliamps is equal to 1 and multiply 35 milliamps by 1. So 35 times 1 divided by 1,000 is equal to 0.035 amps. Remember, we put the milliamps on the bottom because it's the thing we want to get rid of. The amps go on top. Okay. Now we can go ahead and do our substitution step. R is equal to 9 volts divided by 0.035 amps. Resistance is equal to 260 ohms. Are we done? No, we're not. We need to ask ourselves the two questions. The first one, ohms are the units of resistance, so that's fantastic. The next one, is 260 ohms reasonable? Well, the answer is, of course, that if we look at the cabinet of resistors at the front of the classroom, there are lots of 260 ohm resistors, so that's not a ridiculous number. So we can go ahead and underline that and move on. So that second question, I'd encourage you to continue using it before you move on to the next item on the worksheet or on the test. Ask yourself, does my answer make sense? More and more, this will start to be comfortable for you. And if you think that that's only something you would do in school and it's something that would only be valuable on a test, think back to the Gimli Glider problem. The fuel team put fuel, measured carefully the fuel for that flight from Montreal to Edmonton, How many times, how many flights do you think there are from Montreal to Edmonton each day? Do you think the airport crew could have benefited from using the second question there? Absolutely. Hundreds of lives were almost lost because they didn't ask themselves the second question. So something for you to think about. Okay, so let's wrap up for today then. There is no doubt that in science and mathematics we need to be able to accurately convert units. We need to be able to communicate large and small numbers. We need to be able to cope with older units of measure. We need to be able to make our equations fit. And sometimes lives or millions of dollars hang in the balance. The secret to these conversions and being effective is to understand that all you need to do is multiply by 1. And once you know that secret, just be sure you keep the unit you want to keep on the top, the one you want to get rid of, place it on the bottom of your multiplier. And in any case, don't forget the second question. If you do things in the opposite direction, you'll get crazy values like 13.5 meters for a thickness of a dime. And you should be able to recognize when you've made a mistake. All right, go ahead and practice your multiply by 1 technique and the 2 questions on the unit conversion worksheet. Thanks very much, and have a great night.